Prepare for a captivating journey into the unknown. Today, we will lift the veil on one of the most enigmatic phenomena in the cosmos, black holes. You can expect surprising discoveries and unexpected twists that will make you rethink the laws of the universe. Stephen Hawking, a brilliant scientist and an outstanding popularizer of science, left an indelible mark on history. His book, A Brief History of Time, published almost 40 years ago, continues to inspire people to study the cosmos. Like any popularizer, Hawking aimed to simplify complex concepts to make them understandable for a wide audience. However, in one of the issues addressed in his book, the simplification might have gone too far, distorting the essence of the phenomenon. The irony lies in the fact that it concerns Hawking's own scientific work, a breakthrough in theoretical physics, in a paper with the intriguing title, Black Holes Explode. The description of black hole evaporation in Hawking's scientific paper differs significantly from his explanation in the popular book. The simplified explanation doesn't fully reveal the nature of black holes and the reasons why these objects lose their mass. In this episode, we will attempt to approach an understanding of one of the many interpretations of the famous Hawking radiation. Until the second half of the 20th century, few believed in the existence of black holes. This was not only due to their fantastical appearance but also because they seemed to contradict several physical laws. For example, to an outside observer, an object falling into a black hole simply vanishes, meaning any information about it is lost. If black holes exist, they violate the first law of thermodynamics, which states that energy, or information, cannot be created or destroyed in an isolated system. Even more threatening, black holes seem to contradict the second law of thermodynamics, which states that entropy, a measure of disorder in a system, always increases or stays the same, but never decreases. Simply put, ice can melt into a puddle, but a puddle cannot spontaneously freeze back into ice. All matter in the universe contains entropy. But what happens to it when it enters a black hole? Is entropy lost along with the matter? If so, the universe loses some of its total entropy, which contradicts the second law of thermodynamics. Until the early 1970s, this posed a serious problem, but seemingly not for Stephen Hawking. By then, he had already graduated from Oxford University and was engaged in theoretical physics. Hawking's attitude towards the black hole entropy problem was, if black holes don't obey the second law of thermodynamics, then so be it. That doesn't mean they don't exist. Hawking knew there was a connection between the singularity at the center of a black hole and the beginning of the universe itself. He proved this in his early work, developing mathematics showing that a universe dominated by general relativity must have begun with a singularity. Hawking was convinced that the key to unifying relativity and quantum mechanics, that is, the key to understanding the universe itself, was hidden precisely in the centers of black holes. Therefore, even if these strange objects didn't align with seemingly immutable laws of physics, that could be tolerated. In Hawking's view, one shouldn't be obsessed with the laws of physics. Finding the truth about black holes was far more important. However, fortunately, there were people who disagreed with him. Jacob Bekenstein, a graduate student at Princeton University, found a solution to the entropy problem in 1972 by studying Hawking's earlier work from 1970. In that paper, Hawking mathematically showed that the area of a black hole's event horizon never decreases over time. Moreover, when matter falls into a black hole, its event horizon increases. Bekenstein proposed that the event horizon could be a measure of a black hole's entropy. Hawking didn't like the idea of his own work being used for such purposes. After all, if black holes truly have entropy, then they must radiate heat. But this is impossible since nothing can escape their gravitational pull. What happens next? Will Hawking admit he was wrong? And how will this discovery change our understanding of the universe? Stay with us to find out the answers to these questions and unlock the mysteries of black holes. Ultimately, Hawking attempted to refute the theory proposed by Bekenstein, but instead, he discovered a precise mathematical relationship between entropy and the event horizon. Thus, instead of destroying the idea, he confirmed it, making his most significant breakthrough in science. The result was the Bekenstein-Hawking entropy equation, which clearly demonstrates that thermodynamics plays an important role even in such exotic objects as black holes. Based on this discovery, Hawking hypothesized that any object possessing entropy also possesses a temperature and, therefore, must radiate energy. The next stage of his research was to determine the temperature of black holes. In the process, the scientist realized his initial mistake. One cannot describe the workings of the universe based solely on general relativity, which is only part of the overall picture. Another fundamental theory, quantum mechanics, needed to be incorporated. In 1974, Hawking presented his revolutionary scientific paper to the world, asserting that black holes are not eternal but are subject to evaporation due to a peculiar quantum relativistic effect. The classic explanation of this phenomenon is likely familiar to many, and it's what Hawking described in his famous book, A Brief History of Time. The essence is that empty space is never truly empty. It is permeated by quantum fields that exist everywhere, even at and beyond the boundaries of a black hole's event horizon. For illustration, this is usually depicted as follows. In empty space, pairs of virtual particles and antiparticles, i.e. matter and antimatter, constantly appear and immediately annihilate each other. However, near the event horizon, one of the particles in a pair can cross the point of no return, while the other, conversely, escapes, transforming into a real particle carrying energy. To an outside observer, this looks as if the black hole is radiating energy. It's important to note that the particle absorbed by the black hole carries negative energy, which is subtracted from the black hole's total mass. This explains that nothing is radiated beyond the event horizon, which does not contradict general relativity, but simultaneously, the black hole's mass decreases, which can eventually lead to its complete evaporation. Despite the attractiveness of this explanation, questions arise about its accuracy. First, one should not take virtual particles too literally, as they are more of a mathematical construct used by scientists to simplify calculations. Furthermore, this model might give the impression that Hawking radiation originates exclusively from the event horizon, which, as will be shown later, is not entirely accurate. This leads us to perceive the event horizon as some physical entity, a kind of surface of the object that emits temperature. However, the event horizon is merely a region of space, no different from the rest of space except for its curvature. It's simply a patch of space that, once crossed, makes it impossible to escape the black hole's gravitational pull. Therefore, even after crossing the event horizon, an observer would notice nothing special. It merely signifies an inevitable encounter with the singularity. So how, then, should we understand this radiation? To begin, instead of picturing empty space with annihilating particles, it's better to consider quantum fields, mysterious, fluid-like entities that permeate all space. Real particles, such as photons or electrons, are oscillations of these fields, their excitations. The most famous example is electric and magnetic fields, whose oscillations form electromagnetic waves. Quantum mechanics bundles these waves into packets of energy known as photons. This holds true for everything in the universe. There's an electron field whose oscillations create electrons, as well as a quark field, a gluon field, and a Higgs boson field. Every particle in your body is, essentially, a small change in a quantum field. Quantum fields possess energy, and at their lowest energy level, they do not generate any particles. This state of a field is called a vacuum in the modern sense. You can imagine this as two waves, one with positive energy, and the other with negative energy. In a vacuum, these waves interact and cancel each other out. Fluctuations are present, but no real particles exist. However, if you add a bit of energy, everything changes. The field transitions to another energy level. The waves no longer cancel each other, and oscillations appear. That is, real particles. Thus, a vacuum is a field at its lowest energy, in its quantum ground state, while in an excited state, it generates real particles. It's fair to say that the phenomenon of Hawking radiation allows for various interpretations, each with its strengths and weaknesses. One of the most illustrative ways to understand this phenomenon is to turn to a related theoretical concept known as the Unruh effect. The essence of this concept is that the very notion of a vacuum is relative, and depends on an observer's motion in spacetime. Imagine an observer, let's call him Sergei, flying through space in a powerful rocket, constantly accelerating. From Sergei's perspective, he will perceive a temperature proportional to his acceleration. In other words, the stronger Sergei's acceleration, the higher the temperature he will register, as if he were bathed in a sea of photons surrounding him from all sides. But where do these photons come from? It's important to emphasize that they are not a product of the rocket engine's operation or any other traditional heat source. They arise from space itself, from nothing. To better understand this paradox, let's introduce two more observers into our thought experiment, Anna and Vasily. Suppose Sergei decides to visit Anna in his rocket, capable of developing colossal acceleration, reaching 1.5 trillion gs. It's worth noting that the unravel effect becomes noticeable only at extreme acceleration values. Let's also assume that Sergei's rocket is equipped with an advanced protection system that shields his body from the destructive effects of such monstrous g-forces. So Sergei launches, and Anna and Vasily, standing at the spaceport, wave goodbye to him. Sergei will certainly see Anna's hand wave, as she is in front of him in the direction of the rocket's motion. However, the situation with Vasily, who is behind him, is much more complex. If Vasily is far enough from Sergei, the photons emitted by his hand will take a certain amount of time to catch up with the rapidly receding rocket. Moreover, if Sergei's rocket has an inexhaustible energy supply and can maintain constant acceleration, then photons from Vasily will never reach him. Of course, at some point Sergei will have to stop his rocket, and then Vasily's photons will catch up. But as long as the rocket continues to accelerate, this won't happen. A curious situation arises. Sergei feels as if he sees only half of spacetime. Behind him, a horizon forms, a boundary from which light cannot reach him. But what do Anna and Vasily see during this time? From their perspective, nothing unusual is happening. In their reference frames, the universe looks completely normal. However, Sergei is in a different reference frame, and for him, spacetime is divided into two regions, the one he sees and the one from which light cannot reach him, i.e., the horizon. So, Anna and Vasily are in a vacuum, where quantum fields are in their ground state, characterized by the absence of any particles. But Sergei, in his reference frame, sees a completely different picture. The space around him can no longer be described as the ground state of quantum fields. It is no longer a vacuum in the usual sense. What is it then? According to theoretical concepts, the part of space observed by Sergei turns out to be quantum entangled with the part of space hidden beyond the horizon. This is no longer the ground state, but a complex, undefined quantum state that corresponds to a finite temperature. Simply put, it is filled with particles. At the same time, Anna and Vasily see no photons, only empty space and each other. But Sergei sees photons flying towards him. He observes positive energy oscillations that are quantum entangled with negative energy oscillations in the region of space behind him. For Sergei, spacetime looks different than it does for Anna and Vasily. It is filled with particles that are entirely real to him. The concept of the unravel effect is truly captivating. The radiation arises solely due to acceleration. If there is acceleration, there are photons. If there is no acceleration, space is empty. It turns out that the radiation depends on the observer and appears to be a kind of fiction. But let's remember what gravity is in general relativity. Isn't it also a kind of illusion? According to Einstein's famous equivalence principle, acceleration and gravity are essentially indistinguishable. Therefore, it's not surprising that black holes, possessing colossal gravity, have a temperature. Imagine Sergei in his rocket near the event horizon of a black hole. To avoid falling in, he must constantly accelerate. In this case, he will be surrounded by photons arising from quantum entanglement with photons located beyond the event horizon. These photons will be entirely real to him. However, Vasily, lacking engines and thus experiencing no acceleration, will see a completely different picture. Unfortunately, he will not be able to escape his unfortunate fate, and will sooner or later collide with the singularity. But what will he see as he approaches the event horizon? The answer: nothing special. He is not accelerating and will see no photons either before or after crossing the horizon. The analogy between the Unruh effect and Hawking radiation is obvious, and often these two phenomena are considered manifestations of the same physical principle, although there are fundamental differences between them. Let's imagine Anna, an observer located at a significant distance from a black hole's event horizon, at such a distance that she doesn't need to use engines to maintain her position. In the context of the Unruh effect, Anna will not register any temperature because she is not experiencing acceleration. However, according to Hawking's theory, Anna should register a certain temperature, measurable by any distant observer. The exception is Vasily, freely falling into the black hole, who will detect no radiation. This fact highlights a significant difference between the Unruh and Hawking effects. Moreover, for Sergei, located near the event horizon, the required degree of acceleration to maintain a fixed position will vary with distance. Accordingly, the Unruh temperature he measures will also be different, which doesn't entirely align with the concept of Hawking radiation. Gravitational redshift helps resolve this contradiction. This effect is analogous to a car losing kinetic energy while trying to climb a hill without additional power. Photons attempting to escape a black hole's gravitational while also lose energy, although their speed remains constant. Their wavelength increases, and frequency decreases, leading to the photons shifting from the green to the red part of the spectrum. The key point is that redshift is maximal near the event horizon and weakens with increasing distance. Thus, Sergei, in immediate proximity to the event horizon, experiences the greatest acceleration but also the strongest redshift. If he were farther away, he would register a lower temperature and less redshift. As a result, he will perceive the same temperature at any point, matching the radiation temperature measured by Anna. This finite temperature is Hawking radiation, which can be interpreted as positive energy excitations intertwined with negative energy excitations beyond the event horizon. These negative energy excitations lead to the black hole's mass loss, ultimately causing its complete evaporation. Unlike the Unruh effect, which is observed in flat space, the Hawking effect manifests exclusively in curved spacetime. It's important to note that in curved space, observers cannot agree on the state of the vacuum they are in, and consequently, cannot agree on the presence or absence of particles. The previously chosen acceleration of 1.5 trillion gs for Sergei is not accidental. It approximately corresponds to the surface gravity at the event horizon of a solar mass black hole. At such an acceleration, Sergei would perceive a temperature of about 60 nanokelvins, which is only infinitesimally above absolute zero. This is precisely the temperature that Hawking calculated a solar mass black hole radiates. It's noteworthy that the temperature in Hawking's equations is inversely proportional to the black hole's mass. This means that the more massive a black hole, the less it radiates. Unlike ordinary matter, black holes, as they lose energy, do not cool down but heat up. Consequently, more massive black holes take longer to fully evaporate. A solar mass black hole would take a trillion years to completely disappear. This means that no black hole of real mass has yet died, and is far from doing so. The question arises, is it possible to detect black hole radiation? Unfortunately, no, because the cosmos is still too hot for that. The cosmic microwave background radiation, left over from the Big Bang, has a temperature of less than 3 kelvins, which is many orders of magnitude higher than the temperature of stellar mass black holes. Hawking radiation is simply indistinguishable from the cosmic microwave background. However, what about less massive black holes? They should have a higher temperature. Indeed, the smaller a black hole, the greater its radiation. Theoretically, at the end of its life, as its mass approaches zero, the emitted energy approaches infinity. In other words, black holes end their existence in spectacular explosions, emitting high-energy gamma-ray photons. There are gamma-ray telescopes that daily record bursts from various astronomical sources. But could any of these bursts be caused by a black hole? Science knows that black holes form from the gravitational collapse of stars whose mass is at least 2.5 times that of the Sun. This means that black holes of smaller mass should not form in the universe. However, there is a hypothesis about so-called primordial black holes, which could have formed immediately after the Big Bang. These objects have no mass limits, and theoretically could be even smaller than the Sun. It is speculated that some of them might have already evaporated, revealing themselves through radiation. Nevertheless, no such event has been recorded to date. Stephen Hawking believed that the lack of observational confirmation of his black hole radiation theory was the reason he was never awarded the Nobel Prize. Despite this, his work is considered outstanding, and the mathematical derivations are so convincing that black hole radiation is recognized by the scientific community as a real phenomenon. And this is despite the absence of a unified quantum theory of gravity that could describe this effect in detail. The existence of Hawking radiation is virtually beyond doubt. However, while Hawking's discovery resolved the black hole entropy problem, it created a new, more complex enigma. If black holes truly radiate energy and eventually disappear, what happens to the information they contain? Does it vanish with the black hole? If so, one of the fundamental principles of quantum mechanics is violated. On the other hand, if the information is preserved and leaves the black hole, then this contradicts Einstein's theory of relativity. This black hole information paradox remains one of the key problems in modern theoretical physics. Its solution may require the creation of a unified theory of everything. Scientists still cannot reconcile gravity, a fundamental concept, with the laws of physics that govern the universe at the micro level. Stephen Hawking's work is undoubtedly an important clue that may help find the answer to this question in the future.